Okay, great. If you look at the presentation here, what do you think we're going to be learning about?
Gravitational forces and their effects.
Oh, there we go. So, you guys have been doing space science forever and ever. Every term course since you were this you know a lot of what happens, right? So you know the sun revolves around the earth and rotates on its axis and all that. But today we are focusing on why this happens. Okay? So I want you guys to go around this table here. The class of five, if everybody's looking take some space while it moves on the desert flag so that you can actually see. I think move on the side, there's a big better okay. So, when we speak about the fabric of space, you know what I mean, right? You've heard that saying before. So this read is going to be our fabric of space, right? Can I one speak a planet for me? One person, read. Okay, so it's not Timmy. Timmy, go first. I've got a planet. Okay, so I want you to make them move across. We have limited time. We're going to do now. Make them move across the fabric of space. Just let them go and see how they move. So they're not really moving much. They kind of go towards the center because there's multiples of them. But guys, they are going in whatever direction you push them towards. Right? Now, my fabric of space is flat, guys. My fabric of space is flat. So when I add planet or planetoid, it just moves in whatever direction I force it to. So now we have what is called a gravity well. Right? So this is our sun. A gravity well. This is our sun, this is our example. The sun is so dense and has so much mass that it makes a dent or a dip in space. Now, pick one planet for me. One. Okay, ready? Now, ready? Okay, now make them move again. How are they going to move? Okay, ready to start off. You see that going towards the center, right? Now, if we add more force, more inertia, what shape is it moving? A circle. And rotating around the apple. It's making an ellipse rotating around the apple. And our Earth orbits in a what around the sun? In an ellipse as well, right? So does it make sense that our Earth orbits the sun in an ellipse and orbits the sun because there is a gravity well pulling it towards the sun, right? Now I want you to watch the model. Do you think it takes more or less force to put it around the outside edge or around the inside edge? When does it have more energy? Around the outside edge or the inside edge? Outside. It is using energy as it goes towards the center, right? Now, do you see it is also rotating faster the closer it gets to the center? Right. The closer it gets to the center, the faster it starts to spin. Do you see that? Yep. So, what's our closest planet to the sun? Mercury. And how long does Mercury take to make a revolution around the sun? 88 days. And what's our furthest planet? Neptune. Neptune. Does anyone know how long Neptune takes to make a revolution? 156. Guys, 156 years. Right? It's 156 Earth years is 1 Neptune.
Excuse me.
Yes. So it's crazy. Essentially, yes. It is absolutely crazy. And it is because of being distant in relation to the sun's gravity well. Right? So the further away they are, the slower they are rotating around the sun. So the closer, guys, the closer they are, the faster they are rotating around the sun. Right? Does that make sense? But now, why is it that we don't just go crashing into the sun? Gone. Any theories?
Because
Yes. I need hands. Okay, because the earth is pulling us away. So those lines of this, what yes?
so basically, or if that were the case, we would like crash into a black.
Exactly. So the thing is, you are looking at space.
And space. And the thing with space, there's no gravity in space, man. So it's impossible.
Gravity, well. But, okay, wait, I'm going to explain. So, you are thinking of it as 2D. The Earth, the Sun is not resting on space like this. It is essentially falling through space. The Sun is moving away from us at a constant speed. So it is essentially pulling down this gravity well. Pulling down this gravity well constantly. And pulling the other planets along with it in its fall. So well, it's not falling in a sense because there's no down and up in space. It is we are moving away. The sun is constantly moving away from us. And that is why we can never reach the sun to crash into it.
Now, but what happens if it goes to
But does
Then it is essentially infinite. It's going towards the center of the universe.
So we are not pulling the sun out.
the gravity?
I will explain now. Okay, I'm going to count to 5 and everyone needs to be back in the chair. And 5. Okay. So, what is happening is the sun is being pulled towards the center of the universe. Okay, I demonstrated for you guys going down the gravity well, but space is 3D. There is no bottom, no top, no nothing. It is infinitely one. So the sun is being pulled towards the center of the universe, as is the rest of the universe. We are slowly contracting back to our center, right? And because of that, it essentially looks like this. So this would be a side view. So here's our sun heading straight towards the center of the universe, towards what is known as the Great Attractor. I'm not sure what it is. And here are the planets in the gravity world attempting to catch up to the sun. Right?
So what if the sun stops?
The sun won't stop until it reaches the center of the universe.
And what happens when it
When it does, the theory is, during the Big Bang, right? Everything was super dense and super hot. Then it exploded. And when things get hot, right, they what? Expand. Good job. Wait, I'm getting. So, they are expanding rapidly. Now, when things start cooling off, they what? They contract. So essentially the theory is the universe has expanded exponentially and now it is contracting back down as it is cooling down. So everything is contracting back together, back towards the center of the universe.
So you need something getting exploded again.
Exactly, that's the working theory as to why the Big Bang happened and all of that. But it is not fully worked out. Wait, I need hands. Yes.
So it's full theory.
It is, there's a lot of math involved in it, but it is mostly theories because it's very difficult to quantify.
But the math is based on the theory.
Yes.
So when the universe is the universe like expanding every like 1,000 kilometers a second?
Well, there's the theories that it's still currently expanding and that the sun is shooting upwards, and there's the theories that it is currently contracting and the sun is shooting inwards. It again just depends. It is all theories, but those are the working ones we have currently.
Yeah, we'll be dead, man.
Unless you become a scientist and investigate it for us. Well, you should was. Wait, yes. We don't know. That's part of the theory. So, wait, you will get it. So, why do things spin on their axis? So we already spoke about why the sun revolves around the earth due to the gravity well. But it also rotates on its axis. Do we have any theories as to why the sun rotates on its axis?
Yes.
Because so that it can differentiate different seasons.
Okay, that's true. That's one of the effects. But we're talking about why it started. So essentially, the theory we have currently is when the planets formed, there were large meteorites that, due to their own gravity wells, pulled in other meteorites. And each time a meteorite joined, it added force onto the globe, or onto the large meteorite. So it's floating like this, there's a new meteorite that hits it, it goes, and it starts to spin. And there's another one, and it continues to spin, and another one, and it continues to spin. And then after a while, it becomes more compact, and it shrinks down into the round shape that we have, due to how fast it is spinning. You understand? And it continues to spin simply because there is nothing to stop it. Newton's first law of motion: an object in motion will most likely stay in motion unless acted upon by an outside force. Remember, there's no gravity in space, there's no friction, there's no wind resistance. So there's essentially nothing to stop this spin. But even if there's nothing to stop it, things lose energy over time, right?
Yes, ma'am.
So does the spinning lose energy over time?
Yes, ma'am, it will.
Yes, it will. It's very, very slow, but it will. So back in the old days of the dinosaurs, we had 22-hour-long days because the Earth was spinning faster. Now we have 24-hour days because we have slowed down from that. It is slowing down at a constant process. But essentially how that works out is every 50,000 years, the rotation will slow down by 1 second. So do you think, far in the future, our great-great-great-great-great-great-grandkids might have 26-hour-long days?
No.
Yes, because it is continuously slowing down. Yes, ma'am.
Ma'am, okay, so ma'am, you know how like the thing, the earth, it's, okay, when it like circles the sun, right?
Yes,
Wouldn't
it is
that kind
rotating.
of motion keep the earth spinning, like even though it's slow?
No, because it can rotate without affecting the revolution. It can, yes, it revolves around the sun. So yes, it can rotate without affecting the revolution because those two things are much slower. We revolve on our axis much faster than we revolve around the sun. You understand?
So
So
ma'am,
if anything, the revolving around the sun will slow us down.
so ma'am, if the earth rotates, would it disturb the like momentum while it revolves?
Not really. Let's see. Yes, who's making
If an object were to like just randomly appear that was bigger than the sun and would it be like every other planet rotates around it?
Yes, we would get sucked into its gravity well. The sun would also get sucked into its gravity well. But that's again all theory. So then we have the effects of Earth's rotation and revolution. Sorry, so your hands been up for a while. Yes.
Ma'am, with the city here with the like, wouldn't like if the Earth like spun and moved fast and stuff, wouldn't that just like shrink the Earth? Because like, and that's my theory to it. Because like ma'am said, it keeps like when the dinosaurs were around, it was 22 hours. So if you were to even backtrack further than that, wouldn't it the faster it spins? Would it be
Sun
more
compact.
compact?
Yes, exactly. That is the exact same reason why Mercury is so super dense. Because Mercury is spinning so quickly that it does not have the chance to really expand further. So it is so super dense because it is spinning so quickly, and it is spinning so quickly because it is so super dense. So essentially, you are correct to say that the Earth would become less dense the slower it's spinning. Very good. Good point. So then we have the effects of Earth's rotation and revolution. This is easy to mix up, okay? Try and remember it within your mind. Revolution, okay, is 1 year. 1 year is long enough for you to start a social revolution, right? That's how I remember it. And then rotation is how it is rotating on its own axis, like a rotisserie chicken. So, revolution, how it moves around the sun. How it moves around the sun causes solstices, equinoxes, and seasons. And rotation, how it moves on its axis, causes day and night, tides, and wind directions. I'm going to demonstrate each for you now, okay? I need someone to come and be my sunshine. The sun in my life. So you I already gave you a model. Okay. Sounds very slow. Man. So, oh, you said ball. Okay, so you are going to be Mr. Sun. Please do not burn yourself. Well, you stand in the middle over there for me. Like right there. So, first, let's look at rotation. So, it's this time of year, my sun is here. It is rotating on its axis. So, this side is experiencing what? No. Rotating on its axis. So, it's spinning like this. They're experiencing day. The opposite side is experiencing night. Yes. And these middle parts in between, so here's day, here's night, they are experiencing what? Mid-morning, mid-afternoon, depending where they are. Right? So now, my earth is spinning this way. So they're experiencing day, they're experiencing night. They're spinning this way. What are they having? Sunrise. They are having sunrise because they are moving towards where the sun is. The opposite side is having sunset. Okay? Our first half hour is over. We will continue this in our second half hour. Okay? Second half hour, we're going to do revolution. My time with you guys is up. Okay? Bye-bye. Bye. I don't like being a subject. Just open up your one camera. I can't know. Please, no more. So, I did the first half of this lesson with you guys this morning, right? You still remember? Yes. We're busy with Earth's rotation and revolution and effects. Taylor was busy being my sun last time, right? So I need a new sunshine. Me. Okay. Now, you don't need unnecessary nonsense. Aaron, please do not burn yourself, okay? Please be careful. Okay, so last time, I can't recall people are talking. Last time, last time, we were looking at day and night, right? And how day and night works. So, the sun is shining on this side, and the opposite side is having
Night solstice.
No. Night and day. We're going back to night and day. We're reviewing night and day. So, this side is having
Day.
This side is having night. The middle ones are having
Sunrise and sunset.
Exactly. Good job, guys. So, this also affects where the sun hits at different parts of the year. I'm going to review that. Antarctica at the South Pole. Antarctica, if they are tilted this way, are having 6 hours of what? Night. And if they are over here and they cycle around the sun, they are having 6 hours of
Day.
Yes. South Pole, is it the opposite or the same? So this is my North Pole, this is Antarctica. My South Pole is the opposite. They're having the opposite. Correct? So, we spoke about how it affects day and night. Now we are looking at seasons. Okay? Thank you. So, we're discussing seasons, remember? So, my revolution around the sun. What season are we having?
Summer.
Summer becomes
Autumn.
autumn. Autumn becomes winter. Winter becomes spring. Yes, right? And while this is happening for the southern hemisphere, is the northern hemisphere having the opposite?
Yes.
Yes. Now, can you remind me what does the solstices mean again?
It means
I need one person. Many hands.
It's so solstice means when the earth is having a specific tilt.
Yes, 100%.
it's where the seasons have this point.
Yes, they are at their most extreme points. So, remember, the earth is not floating around the sun like this. Okay, it's not straight. It's at its tilt. So this tilt is what gives us solstices. Right now, if we are tilted like this, is South Africa, please hold with both hands. I really don't want to hold myself sweet. Okay, if South Africa is tilted like this, are we having a summer or winter solstice?
Summer solstice.
Yes. And the north is having a
Winter solstice.
yes.
Man, can you ever get a report to a solstice?
I'll talk to you about that now. It's a very good observation. Now, the opposite. If we're talking like this, what solstice are we having? And they are having summer. Yes. So, to your point, we don't have autumn solstices, but we do have autumn equinoxes. Right? So the equinoxes are these little parts of the year. Because notice, now my tilt is going this way. It's not tilting towards the sun anymore. So would you say there's an even amount of light? Not an even amount of light, hitting the equator. So it's all shining on the equator rather than more on the top or more on the bottom. Right? So this is an equinox. Remember solstice, we said we're going to remember by saying solstice, solar, sunlight, equinox, equal. So it is equally shining everywhere. So we're going to go through the cycle again. Summer solstice becomes autumn equinox, because now it is directly in the middle. Okay? Becomes winter solstice, becomes spring equinox. Good job! So, our equinoxes, remember, solstices are June 21st and December 21st or 20th, they're around. So it's our most extreme points in the season. In June, are we very cold?
Yes.
In December, are we very hot?
Yes.
So you can feel the most extreme parts. And the equinoxes are right in the middle. So March 21st and September 21st. We had September recently, right? And that was becoming what for us? Spring. So we were having what equinox?
Spring equinox.
Yes, 100%. Any other question?
So you know sometimes like let's say in June it's like winter and it's cold those things. But not every single day would be like real.
Yes.
So and like sometimes the sun will be shining bright and it will be very, very hot. How is that like?
Like it's differences in weather as well, depending on clouds and moisture in the air and all of that. There's some videos attached that you can watch about that. You can check all throughout the PowerPoint presentation. There's different video links. These different video links go more in depth. We need to go through the bases first before we go more in depth. But yes, like you are correct that not every single day in winter is cold and not every single day in summer is hot. Thank you, Mr. Sunshine. Very sunshine. So, next we are looking at tides, right? Tides are caused by what? The Earth's rotation. The Earth's revolution. Is it rotation or revolution?
Rotation.
Rotation. It's rotating like a rotisserie chicken. So,
Why are you looking at me now?
guys. So, I want you to look at this illustration. Let's ignore the sun for now. We'll talk about the sun later. He's scattered. On this side, we have this bubble that is being pulled up by who? The moon. And on this side, we have another bubble of water. Why do you think this bubble of water is here?
Great and Earth's
Yes, 100%. Good job. You did more. So, this side is experiencing more gravitational pull of the water than usual. So it is all going up and forming a bulge. This side is experiencing less gravitational pull than usual. So it is all falling together as if almost to fall off of the Earth. It's all joining together because of its own gravity and the Earth's gravity. Right?
That's right.
So we say the tide comes comes in and the tide goes out. That is not accurate. We go in and out of the tide. It does not. So, our example would be, remember, it's kind of an egg-shaped bubble around the globe. So where are we? There we are. So here's my one side of the egg, here's the other side of the egg, and there's us. Now, we are rotating into the bubble. So what tide are we experiencing?
High time.
High tide. Good. And when we rotate out of the bubble,
Low tide.
low tide. Then we go back into the bubble.
Yes, then my question is like the bubble, you can see the bubble is from the side. The side is like pulling, and the side is like trying to even it out with the other one. So then my question is, as the earth is turning, how do you in and out of the tide? Okay, this is a bubble about my skin. We are stuck to the bubble.
Because remember, inappropriate, you can also move. It is not a solid bubble, okay? It has 2 points, kind of like an egg, right? So now, these 2 points are constant during whatever cycle the moon is in, because it's affected by the moon. So, remember, our moon doesn't rotate on its axis, it stays still. And the moon gets brighter or darker and has different phases due to the sun reflecting off of the earth, right? So dependent on where it is, you'll be able to see the different phases of the moon. If my moon is over here, and my sun is over here, the sunlight is reflecting directly off the earth and directly full onto its face. So that's a full moon. If my moon is over here, the sun is directing there and hitting there. So it's only highlighting about this part of it. So that is a waxing or waning moon, depending on where it is. And if it's over here, the sun can't reach it. So it's a new moon. You understand? Now, that positioning also really affects the tides. Because if my moon and my sun are on the same side, do you think that's going to make, please stop talking, that's going to make the tides more or less extreme? More. My moon and my sun are on the same side.
If the moon and the sun on the same side,
It's gonna have more magic because then now there's a full moon and then there's those tides of the night.
Yes, because the sun and the moon are pulling together. So, the sun and the moon are then pulling together. Remember, the moon is still the strongest one here because it's closest to us. The moon has 2 times more pull than the sun, but the sun is still affected. So now, the sun and the moon are pulling in the same direction. Do you think my other side of the bubble is going to be just as extreme to try and balance it out? Yes, because now there is even less than usual gravity because there's no sun, there's nobody there. And here in the middle, do you think it's also going to be more extreme that there's less water in the middle?
No.
Yes.
What about all the water that's being pulled to the sides?
No, but you sit on the top.
In the middle over here, so here it's pulling, here in the middle. Yes, there's going to be even less water than usual because there's even more than usual being pulled into the sides. You see? Yes.
Also, I'm saying there are different types of oceans, and I think they are fine, right?
For that is not
No, I'm saying that so the tide, man, it has something to do with the tide, and it has to do with the tide. Man. So is the water like pulling from one section of the other?
remember, the moon revolves around the earth as well. So depending on where the moon is, that is dependent on where the bubble is going to be. You understand? So the bubble changes every time the moon phase changes. Okay? Right? Does that make sense? So when it's all on one side like this, and it's extreme tides, this is a spring tide. It's very dangerous to swim during a spring tide because number one, there is a lot of ocean activity happening, all the sharks are out, all the squids are out, everybody's hungry. And number two, the tides are way more extreme, so you are way more likely to have a water-related accident. Right? But now, I want to ask you this question. If my moon is over here, and my sun is over here, my water bubble is obviously going to be there, right? Now that it's pulling in 3 different directions, do you think it's even out a little bit?
Yes.
Yes, there's not one big extreme, right? It's evened out a little bit more because it's more evenly distributed, right? This is when the moon is at waning quarter or half quarter because remember, sunlight reflects, bounces off, highlights this half of the moon, right? This is known as a neap tide. I want you to say it with me. Neap. Come with me. 1, 2, 3. Neap.
becomes like leaf. So me is when it's relaxed, it's more in the middle, it's fine. Springtide is when it is high and hectic. Okay, the whole slideshow, oopsie, the whole slideshow is available to you, okay, on Google Classroom, with the links, with everything else. It also has your rubric for this activity that you're about to do with me, okay? So, for this activity, what I want you to do is I need you to draw the Earth's path through the universe for me, okay? Please, just, wait, let me explain, breathe, it's not difficult. So, number one, these instructions are also on the classroom. Number one, I need to see how the Earth how the Sun is traveling through the universe. Okay? How's it traveling through the universe? Come, ask me. How's it traveling through the universe? The Sun.
It's going to.
It's going to the center. Very good. Okay.
I'm trying to
Then number two, I need to see how the Earth is revolving around the Sun. Okay. Remember, revolving, revolution, how it's traveling around it during the year. Then number three, I need the Earth's rotation on its axis, right? Okay, so I need you to label all of these for me, and I need to be able to see them illustrated in one picture, right? You can find different ways to do this. Use your creativity, everything is for creativity. But an example might be, draw this, there's a block around this one, and you zoom in, and you show me, yes, this is how it's rotating, right? But for all of these, I need effects as well. So, the sun's travel through the universe does what to us? It attracts us towards the sun, it keeps us in orbit, and it's pulling us towards the center of the universe. The Earth revolving around the sun throughout the year does what to us? The seasons, solstice, and equinox. Yes, I will also put them on the board so they can do this stuff. Then the Earth's rotation on its axis causes day and night, and tides. You are correct. So, this all needs to be labeled and in color. Right?
Like the sun, the solar system, then the earth, we draw the earth's height in order.
You can draw it in any way that makes sense for you, because this is for your notes that you're going to use in the future. As long as it is visible to you, the sun travels through the universe, how it revolves around the sun, okay, and how it rotates on its axis. That's what I need to see from you. But you can express it in any way you like. This is just the easiest way to do so. Understand? Anyways, I'm going to give each of you a piece of paper, and our lesson is almost over. So you're going to do this for me for homework. Do you have time in the next class, or is this for homework? It's our next class together. Okay, so Ms. Masana is being nervous, and you're going to be allowed to finish this in our next class that we have together, right? But for the few minutes that we are there, I'm going to distribute papers and give you things. And just give it to the next So I know what you need to do, guys. Vixen won't be here on Friday. So, Miss Vixen won't be here on Friday. Guys, know what you need to do. Your rubric is there. This entire PowerPoint presentation is there. The extra videos are there. The instructions are there. If you don't know, go look on Google Classroom. I promise it's there.